All right, thank you everybody for coming. For those that are online, I'll be monitoring the website, so if you have any questions, please feel free to ask it there. It's my pleasure to introduce Arindam Jati. He is from University of Southern California, from School of Engineering. He joined us this summer for his 3-month internship, and this is his final talk on audio retrieval.
Thank you, Dimitra, for introducing. So I'm Arindam, and as my today's topic is supervised deep hashing for efficient audio retrieval. But before we start, Dimitra already introduced me, but just to let you know that I am from this Signal Analysis and Interpretation Laboratory, SAIL, and my advisor's name is Professor Srikanth Narayanan, or in short, Sri. And so this is our today's agenda. So I will start with the basic definition of audio event detection and classification, and kind of tell you some really nice applications. Then I will move to audio retrieval and ranking, and I will say why that is important. Then we will do some literature survey about retrieval and ranking systems. Then I will move to efficient audio retrieval with hashing, where I will introduce some algorithms. Some of them are supervised, some of them are unsupervised. Then we will see the experimental setting, the results, and the conclusions. So let's start with audio event detection and classification. Generally, it is defined as the human-like ability to identify and relate sounds from audio. Generally, audio events are annotated by humans, and when during annotation process, the annotators provide semantic label for the sound events, whether it's a violin, whether it's a bark, or whether it's a sound of an engine. And it is a common practice to follow an ontology or hierarchy information during the annotation, because it's kind of easier to annotate the coarse class first, then the fine-grained class. For example, if I have a sound of things, I can first identify, okay, it sounds like some engine, then I can go into like, okay, this is a particular motor or something. Now, this is a very high-level overview of an audio event classification system using deep neural network. So generally, we have a pool of audio events and their labels. For example, here we have 3 audio files with bark, alarm, and car engine. And we extract some kind of features like spectrogram, and then feed them into a neural network and try to predict the human annotated labels. This is the simple overview of a training or learning process. Now, after the training is done, we save the model, and we can use the pre-trained model for some inference task or some testing. One of the very simple testing would be, we have an query audio, and we try to predict its level. For example, for this audio, we can predict some confidence scores, like it's like 95% confidence, it's a bark, and 4% confident, it's a cough, like that. We can also do another kind of inference task, and which is relevant to our applications here. And this is called, this is something that we call extracting feature or extracting embedding for a new audio file or any audio file. So after the model is trained, we can have any audio file, and we can pass it through the pre-trained model, and we can extract output of an intermediate layer and use that as an embedding or distinctive feature representation of that audio file. Since this model was trained to classify different audio events, this embedding should have features which are distinctive to different audio events. So there are some open source models like that. One of them is Google's VGG model. And we can use this pre-trained model for our specific applications. Okay. So this is the basic pipeline. Now we can go over some real-life applications of audio event detection and classification. And one of them is definitely the accessibility feature it gives. And we all know that Microsoft Soundscape is a product from our team. And also there is a project going on called Hearing AI. Morayo is working on that. So the basic idea is to provide some kind of accessibility and listen to the environment and try to identify different audio events and somehow let the user know that what audio events are going on in the environment. Another application would be autonomous driving, where the self-driving car can detect different sounds and, for example, some emergency vehicle and kind of take some decisions based on that. And also smart cities, crime prevention, smart homes, we have applications of audio event detection there. And this is like more relevant to our application. And it's like audio content understanding and retrieval. This might have like sub-applications, and one of them is like browsing. So for example, in Bing search, we have this search by image, where we can upload an image of coffee, and we can get two things. One is it takes text labels that it says that it's a coffee, and that's like image recognition. And another is like a bunch of other pictures which are similar. So we can kind of think about similar applications with audio, where we can have a query audio and try to find which audio it is and try to find other similar audio or sounds. One more applications of retrieval is creating multimedia, for example, games or movies. So this is like one scene of a game. And now when the game is designed, that particular scene might have requirement of some audio. For example, here we might have sounds from birds, some footsteps, and when sound engineers add these sounds, they generally understand the scene and search in an audio database and listen to the audio and put a suitable sound into the content. Now this searching can be partially or fully made automatic. If we have a good audio retrieval system with using text query or even audio query, we can make this process partially or fully automatic. So this kind of tells us that audio retrieval is important, and making it fast for search, like real-time fast, is also really important. And that's the whole motivation of this work. So before like starting audio retrieval, I would just like to give an overview of the research areas in audio event detection so that we can see why we lie before we jump into that. So one of the important research area is finding better feature representations of the audio, and with powerful machine learning models, especially DNNs. And this is kind of well explored. It's still being explored, but we have some open source models like VGG or all this TLWIC that can give you powerful audio representations. Another research area is hierarchical audio events. So as I said earlier, audio events generally lie in a hierarchy, and it would be really nice if the model can back off to a coarser class when it fails, because models sometimes fail to detect the very fine-grained class. Then it might have the option to back off. So there are some past work on this, and those are on bi-level hierarchy. But like for any arbitrary hierarchy, it has not been explored yet. The third applications, which is relevant here, is efficient retrieval and ranking. And to the best of our knowledge, it has not been well explored. So let's see what are the challenges for efficient retrieval. First of all, there are millions of sounds, almost like infinite number of audio events available in the internet. So possibly our database will have millions of sounds as well. And there is no established meaning of distance between two sound files. So what people generally do, they get some kind of high dimensional feature representations of the audio events using any of these like VGG or TLVIC, and then try to compute distance between audio events. Now the problem is that since these are high dimensionals and since we have millions of sounds, this distance computation become very expensive. So that's where the need arises to create a very efficient system for retrieval. Okay, so let's jump on that, audio retrieval and ranking. And this is a high-level view of a pipeline of audio retrieval system. And we have a query audio, and what we get some kind of fixed dimensional representation like VGG. And we also have a database which might have millions of audio events, but we store the fixed dimensional embeddings for the database. Now, for the query audio, we basically compute distance between this query audio and all of these audio files in the database. So we do some kind of exhaustive distance computation, and then based on the distance values, we can rank the retrieved results. So if we want to see where the maximum amount of computation is being done, that's basically in the exhaustive distance computation part. So what we will do, we will try to optimize this part as much as we can. And this can be done using some kind of hashing, or in more specifically, some kind of quantization. So the basic idea about hashing or quantization is that instead of storing the floating point audio embeddings, we can store some kind of hash codes, some kind of binary codes, or in quantization term, some kind of discrete values that will help us to make this process fast, the distance computation. Okay. So based on this overall pipeline, we can kind of formulate our problem. So our goal is to come up with a efficient distance computation, and instead of like searching exhaustively in the database so that we can get very accurate result, what we will do, we will do a trade-off. So we will not get the exact neighbors, we will get the approximate neighbors, but because of that, we will be able to do it very fast. So this whole thing is called approximate nearest neighbor search. And a very simple example will be some kind of quantization. So let's say we have a bunch of samples here, and what we can do, we can just discretize them. So let's say we discretize them to 6 centroids or something, some kind of clustering. So since we have, like after we have discrete values, we can make the distance computation very fast. What we can do when a query y comes, we first assign them to a closest centroid, and then when we assign them to the closest centroid, the exhaustive distance computation becomes computing distance between these 6 centroids. So since everything is discretized, quantized, so this like floating point distance computation can be done now by a lookup table, because this centroid is fixed during the training process, and we can compute the pairwise distances and save them in a lookup table. So during query, we can just find that from the lookup table. Okay. Now, this is a very simple example of doing that via quantization, but we will use some sophisticated algorithms that I will come to those algorithms later. But in general, we can divide the algorithms into 2 clusters. One of them are unsupervised. That means they don't need any labels of the audio, human annotated labels. They don't need. So that's the good part. But the con is that since it cannot incorporate human knowledge, it might not retain the data similarity or the data pattern in the hash codes. So there is another types of algorithm that's supervised. So it needs data labels, audio labels, annotated by humans. So the benefit is that it can preserve the data pattern or the similarity between similar audio events and dissimilarity between different audio events in the hash codes, eventually which will help us to get better retrieval accuracy. But the problem is that we need annotators. Yeah. So based on these like 2 types of algorithms, we can do a little overview of the literature that is available. So the first one is the unsupervised one, and it's called product quantization, and it's one of the state-of-the-art quantization or hashing algorithm. So it is inspired by vector quantization, and it basically improves vector quantization by a simple divide and conquer approach. The rest of the 3 algorithms, they are supervised algorithms. The first one is called CNNH, and as you can see, it kind of does the hash coding and the feature learning things in 2 different stages, and then combines them together later. The next one is called DNNH, and it basically an improved version of CNNH, where they do the feature learning and hash coding together and jointly learn the model. The last one is the one we will use, and they have 2 different variants. They are called Deep Quantization Network, DQN, and they also jointly learn the labels, the data pattern, and the hash codes, but they also have a formal control over the quantization error. They literally minimize the quantization error during the training process. So we will use this method and the product quantization, and I will discuss them in detail later. Okay, so let's move to efficient audio retrieval with hashing and kind of introduce the unsupervised algorithm. So let's discuss about some preliminary. So why the exhaustive distance computation is so expensive? So we want to compute nearest neighbor using Euclidean distance, and let's assume we have n samples in the database, and d is our feature dimension. And what we want to do, we have a query x, and we want to find its nearest neighbors So what we have to do, we have to calculate distance of x between all these n samples and sort them. So that's basically the minimum distance of x and y I. So if we take an example, so before going to that, so the complexity is order of nd because we have d-dimensional feature and we have n samples in the database. Now if we see an example where n is the number of samples, which can be 1,000,000, and d can be 1,000. That's very standard. So the complexity becomes order of 1,000,000,000 because it's nd, and that's a problematic thing. So that's where we want to focus. We want to reduce this complexity of searching, and we will see. So this phenomenon is also known as like curse of dimensionality in machine learning community. And after the hashing algorithm, we will see that we can achieve around order of 9 million computation. So from 1 billion to order of 9 million computation. Okay. So let's do some more preliminary. Since product quantization, which is the algorithm we will use, it's kind of inspired from vector quantization. So we just want to kind of review vector quantization first. So in vector quantization, our goal is to convert every feature into some kind of code word, some kind of hash codes. And the method we use is very simple. It's basically k-means algorithm in the step 1. So we have d-dimensional features, and we do k-means clustering here. Let's say k is 8. So we have 8 clusters after the algorithm. In the second step, what we will do, we will quantize every sample. So we'll assign every sample, or we'll approximate every sample with their closest centroid. So all the samples will be approximated by 8 centroids. Now, so if we have k centroids, for example 8 centroids, we can just represent those 8 centroids by like number 0 to 7. So for example, sample 1 might belong to the 4th cluster. So we will denote sample 1 by 4. That's 100. That needs 3 bits. So if we have k centroids in vector quantization, we need log of k base 2 bits to represent the hash codes. So our hash codes will be log of k bits. Okay. So based on this simple idea of vector quantization, we can move to product quantization. The main problem of vector quantization is that it cannot support exponentially large number of code words. So what I mean is that since we need like log of k bits, so if we need 64 bits codes, k will become 2 to the power 64, and that's a very large number, and k-means algorithm can become intractable in that situation. So because of this problem of not supporting a large number of centroids, what we do simple divide and conquer. So we have original feature d, and we divide them into m subspaces. Here m is 3. So just linearly divide them into m subspaces. And so each of these subspace has a d by m dimensional feature. And we do independent vector quantization in each of the subspace. And then we will somehow combine the results together. So we have d-dimensional feature, we first divide and do independent vector quantization. Now, when a query audio comes here after the product quantization algorithm is done, so first it comes here, then it kind of gets divided into different subspaces, and in each subspaces that might get a particular cluster. So if I have 8 clusters here, 8 clusters here, 8 clusters here, we can like choose any of them from each of the subspace. So in general, the total number of code words or centroids, it can be 8 cross 8 cross 8. So it's like Cartesian product of all the code words. That's why it's known as product quantization. So just to kind of keep in mind, so we have M subspaces here, and each of dimension D subspace, which is basically D by M. And K subspace is the number of centroids in each subspace. Typically, it's like 256 or even lesser than that, 128. So these are the two terms that will come, D subspace and K subspace. So the effective codebook size becomes the Cartesian product of all the codebooks, because we can choose one from there and one from there and one from there. So the size of the effective codebook become K subspace to the power M, and that's where it supports exponentially large number of code words. So just after just keeping this in mind, we can kind of see the bigger picture where we are moving from Euclidean to VQ, vector quantization to product quantization, and then eventually in DQN. So we can just see them column wise. So first in Euclidean, for Euclidean computation, we already saw that the expense is like order of ND, and the pros is it's the most accurate because it does exact distance computation, but the con is that it's expensive. In VQ, we saw, since we discretize everything and ultimately distance computation becomes computing distance between the query and the centers, so it becomes order of KD, where the number of centers is number of code words is K. So it's very simple to implement. It's a very simple algorithm, but the problem is it cannot support exponentially large number of code words. And if it does not support lots of code words, eventually the quantization error will be high. So we moved to product quantization, and it can be proved or it can be seen in the paper that the exhaustive distance computation is order of NM plus K subspace D. N is the number of samples in the database, M is number of subspaces, K is number of centers in every subspace, like 256, and D is the feature dimension. So if we can see that N is not multiplied with D here. So that's where we are gaining. And if we want to compare with VQ, it can support a lot of more code words than VQ. Now, just to go to, yeah.
I have two questions.
Yeah.
First, why is the number of effective code words for PQ K to the M instead of KM?
Yeah.
It's divided to like M partitions, right?
Yes. So yeah, that's a good question, because so here, let's say this is the full dimension, and we divide it into 3 parts. Now, in every subspace, let's say I have 8 centroids. So the number of, so I have 8 centroids here, 8 centroids here, and 8 centroids here. So for each centroid from the first subspace, I have the option to choose 8 of them and 8 of them. So it becomes 8 multiplied by 8 multiplied by 8. That will be number of possible choices. Yeah. Yeah. So for example, a query audio might have the first cluster from here, the 4th cluster from here, and the 8th cluster from here.
Well,
and
can you go to the next slide then?
Yeah.
It's you're counting the number of code words, right?
This is the effective number of code words.
So you can basically combine
Effective codebook size, yeah.
You can combine any cluster, like any centroid within each one of M partitions with any other centroid in
Yes.
partition.
Yes.
Correct.
So that's the effective number of code words. So the good thing is that, So this is very high. Let's say it's 256 to the power 8, right? It's very high. The good thing is that we don't have to store all of them, because we only store 8 of them, 8 of them, and 8 of them. But the number of choices becomes 8 cross 8 cross 8. So that's where it is gaining thing. Yeah.
And the second question
Yeah.
I have is the complexity for PQ looks like it depends on your data set size, right?
It depends on the feature dimension.
You have
Also the number of samples. Yeah.
Isn't that bad?
Yeah, it's bad, but this is exhaustive distance computation. I will also there are algorithms for non-exhaustive distance computation. So what I'm showing here, it's still computing exhaustive distance. So basically, computing distance between query and all the samples in the database. But there are algorithms. I will talk about it in future works, which where we can incorporate these product quantization algorithms and DQN algorithm with the non-exhaustive distance computation. There is a off-the-shelf algorithm there. But yeah, so even with exhaustive distance computation, we are gaining like this much. That's the benefit. Yeah.
Because M is very small.
Because M is very small. The maximum value of M is number of subspaces. Generally, people use like 8 at most.
Okay.
Yeah.
What if the dimension of your data is also small? Then we don't need this.
Yeah, if the dimension is small, we don't have cards of dimensionality.
Right. Yeah.
So we don't need this. Yeah.
So this is mainly for high dimensional.
Mainly for high dimensional features. Yeah.
Yes.
Okay. So let's come back to the example. So we had this top two lines. So 1 million samples in our database, and 1,000 is our feature dimension. Now, just keep in mind these two more things here now. So let's say the number of subspaces, M is 8, and number of centroid per subspace, K subspace, is 256. Now just these 4. Now, based on this, if we want to calculate the complexity, as we saw earlier, Euclidean becomes order of a billion. Now VQ, if we want to like have the same number of code words as PQ, it becomes intractable, because the total number of code words becomes 256 to the power 8, and if we want to have similar number of code words, vector quantization becomes intractable. But PQ is not, because it does divide and conquer, and it can be calculated that it becomes order of 8 million. And so that's a big gap, and we will see what will happen in DQN. Yeah. So this is the overall system again that we kind of discussed earlier, and we told that we have to optimize the distance computation part. So now we have an algorithm that we can use. We have product quantization that we can use on the full database to train, and after the training is done, this is done offline. After the training is done, we can store the code words. And when a query comes, instead of doing Euclidean distance computation, we can use product quantization algorithm to compute the distance with the query and these code words. So we save some computation here. And the rest of the ranking system is similar. Okay, so now let's move to supervised defashing. So just to recap, the reason for moving from unsupervised to supervised was we want to incorporate human knowledge into the hash codes. So we need some level data, but after incorporating those knowledge, we can have hash codes that can have similarity, data similarity in the hash codes embedded into them. And so the overall picture is similar. We just replace this offline portion. So we have an audio embedding database, and all of the audio in this database might not be manually labeled. So we can take a part of the audio database that is manually labeled and do supervised hash code learning. But after it is trained, we can generate hash codes for the full database. As much as level data we have, it will be better in general. But after the training, we can generate hash codes for the full audio database and store them in our code word database. So the good thing is that this database can keep increasing, because we can have more audio and we want to put them into the database, and this might have level, might not have level, but in general this database can keep increasing. And in the distance computation part, we can use some supervised hashing algorithm instead of the product quantization algorithm. Okay. So the algorithm we use is called Deep Quantization Network, and as I said earlier, the main contribution was to do hashing and feature learning together and to have a formal control of the quantization error. And if we want to see from the left, we will have an audio pair. So for example, they can be from the same class or from different class. And we pass them through some kind of feature extraction module, either VGGish or some TLWeak, and then after extracting the features, we can pass them through a neural network. And in this case, it's a simple multi-layer perceptron. And after the forward prof at the outermost layer, we compute the loss, and we have two losses here. The upper one is pairwise similarity loss, and it basically increases the similarity, cosine similarity, if these two audio are from the same class, or decreases the similarity if they are from two different classes. So it kinds of retains the data similarity. The second part is basically the hashing part. So it also does product quantization. So as a hashing algorithm, it uses product quantization, and it calculates the quantization error or quantization loss. So for some specified bits, for example, I want to train this model for 16 bits. 16 bit is, by that I mean after training, every feature can be represented by 16 bits. So for 16 bit, I can do the forward pass, I can compute the cosine loss. I can also do a product quantization for 16 bits and calculate the quantization error. And then I can add these two losses with some weight parameter and minimize that through backpropagation. Now, so if this model is able to decrease the quantization error, so we can see it kind of increase the quantizability of these green embeddings. So that's the whole process. Now, if we come back to that comparison slide, so we left this blank, the portion of the DQN, and we can see that so this DQN, it has a forward pass over this network, and it can be a specified size according to applications, and after that it does product quantization. So during testing time, it has to do forward pass and product quantization for inference. So the complexity, it becomes equal to product quantization plus an added term, which is the DNNX. And DNNX is basically the complexity of doing one forward pass for one sample. And so it depends on the size of the DNN and number of hidden layers you have, because it has to do some matrix multiplications. And if we come back to our original example, so and put them there and use our DNN size, then we can come up with more or less this figure. So we can do it in order of 9 million operations. Now this forward pass of DNN or DNNX, this is basically matrix multiplication, and here I use the brute force matrix multiplication. But there are more efficient matrix multiplication techniques, and also we can use GPU if needed, and this can be reduced more. if we use sophisticated algorithms.
So your DNNX, does it depend on anything on your data size or on your feature size rather than
Yes,
just the
it depends on the feature dimension and the size, the structure of the DNN. Yeah, number of layers, and because the more layers we have, the more matrix multiplication we have to do. That's a nice question. Okay, so it's kind of similar to PQ, but it cannot be generally lower than PQ. But it like depends on the DNN architecture. Okay, so yes.
Is it less accurate? These models
Which is the least
less
accurate?
accurate.
So this is the most accurate.
Yeah.
And, the least accurate. So VQ becomes intractable if we have a large number of code words. So if we want to compare like PQ and DQN, DQN will be more accurate because it's supervised, because we use the human knowledge there. So we will see that DQN will boost up the performance even if we have a very small amount of training data compared to the whole size of the database. Yeah.
Harry, can we go back to the block diagram?
This one?
Yeah, you mentioned your in PQ, you're dividing your dimension into m
Yes.
partitions, right? Where does it happen here? Like there?
Yeah, it
partition?
Yeah. So we take this embedding. So now this becomes our input to the PQ algorithm.
Okay.
So this becomes the input of our product quantization algorithm. At every epoch, we do a product quantization and calculate the quantization error
Okay.
after every epoch.
So the difference between DQN and PQ is DQN uses PQ
Uses PQ
for
inherently.
quantization and do it in a supervised way.
Do in a supervised, exactly.
With the pairwise cosine loss, that's also there.
That's also there, yeah.
Okay.
Yes. That helps to retain the data similarity, but the whole hashing part is done by product quantization.
Does it work without the cosine loss?
So if we don't have a cosine loss, that's basically doing PQ after some
Yeah.
non-linear transformation.
Yeah.
So, I mean, it will work, but I am not sure whether, we will have any application for that, because PQ in general is very efficient and state-of-the-art algorithm. So why not apply PQ directly on the larger features?
Well, but in this case, you have a supervised system, right? I'm
Yes.
just saying removing the cosine loss and keeping the quantization loss.
So you mean if we remove this part and just have the quantization loss, right? Yeah. So the thing is that this quantization loss, this does not need any level. So only supervision that is useful is in this cosine loss.
But you have label data set, right?
Yeah. But product quantization algorithm itself does not need levels. It's basically k-means clustering, sophisticated k-means clustering.
Yeah, it doesn't need it, but
Yeah.
because you have it, you can have one that's basically you can have one that's supervised and one that's unsupervised.
Okay.
Compare the performance.
Okay.
If the supervised.
Oh, you mean instead of cosine laws, we can have some prediction of the level or something?
No, just training with quantization loss.
Okay. Yeah, maybe. We will discuss this offline better. Yeah, it will be better. Yeah, I'm not getting exactly the architecture you are thinking. Yeah. Yeah. Okay. Any other question before we move to the experimental results? Okay. So. Yeah. So we have two data sets for evaluation. One is DCASE 2018 task 2, and which has 1600 test audio files and around 10,000 training audio files, and it has 41 classes. So here are some examples of the audio that I took from the DKS dataset. So let's see some of those and try to predict whether we can see. So this is an acoustic guitar, and this is a cello. This is scissors, and can anyone guess that? Oh wow! Wow! Wow. I thought that's the most difficult one. That's why I put it in the end. Okay, we don't need machines then. So we also tested on ESC50 dataset. That is kind of a little bit smaller than the DKS dataset. And for features, as we discussed earlier, I use VGGish, and I use mean over the temporal dimension. So it's 128 dimension. And I also use TL week. So this is not acronymed as TL week in the paper. There is no acronym, but you can just see the paper here. And its dimension is 1024. And the evaluation metric is called mean average precision, and at R. So this R is basically the number of retrieved items. And different applications might have different different requirement of this R. Someone might be interested in the top 3 results, some browsing might be interested in the top 10 results, or some applications might be interested in all the retrieved results. This is the R, and the average precision is basically number of positive retrievals, number of hits that are correct. And mean average precision is mean over all the test queries. So this map at R, it varies between 0 to 1, and most importantly, it depends on the ranking or order of the retrieved result. So if all the hits are correct and all the hits are like ranked at the beginning of the list, the map will be 1. So let's move to results, and so we calculated map over the full database size as our metric. So the reason is that this is a very standard metric, first of all, calculating it at the full database size. The reason is that if some retrieved hit is at the very end, it generally penalizes it very much, but we want to see, even then we want to see where it lies. So if we calculate map at 3, it will just discard all the retrieval results after 3. So we use 2 features, as you can see, and all the unsupervised algorithms, they are trained on the full database because they don't need levels. And the supervised algorithm, DQN, it is trained on 10% of the database. And more specifically, I selected 20 samples from each class. That kind of gave around 800 samples, and it's around less than 10% of the full database size. So we are assuming we don't have levels for the 90% of the database. Even then, we will see improvement. So first, among the unsupervised models, we can see PQ is better than some baselines, and some of them are like spectral hashing, iterative quantization. These are the we applied like multiple baselines, and these are the like best performing baselines. So even then we can see PQ is better, mostly for lower number of bits. And when we go to supervised model, we can see that even having a small amount of labeled data, we can increase the map performance by a significant margin. We also got same findings in the ESC50 data. So I'm skipping it for the sake of time. So here it's a very busy plot, but let's first focus on the red lines, which is basically VGGish 128 features. So what we are doing is, we are in the x-axis, we are increasing the amount of labeled training data we have. So we start from like 10%, less than 10%, and we eventually increase the amount of labeled training data. And this y-axis is basically map at the full database size. So we can see when we increase the level data, the general trend is to get better retrieval accuracy for both the VGG features and also the TL weak features. Another observation is that, so if we only consider one type of feature, let's say the red one, when you move from 8-bit to 16-bit, there is a very high gap. And this is because based on our parameter values, 8-bit is basically having one subspace. So it's basically vector quantization. And when we move to 2 subspaces, we gain a lot, but after that it's kind of getting saturated.
So,
Yeah.
if you use half of your data set
Yeah.
or versus the full data set,
Mhm.
there's not much improvement
Yeah, there is not much improvement
for the VGG. Okay.
for the VGG. So I was also looking into that, and what I kind of my hypothesis is that our model is really tiny. It's basically 2 layers, 256 and 512. Yeah. So this tiny model is like good for this amount of data, like 800 samples. But when we reach here, we have like 10,000 samples. So we might like having a bigger model actually might help in that case. But having a bigger model here might result in overfitting. So if we really have all the data leveled, we can just use as big model as we can. Yeah. Here is another ablation study, and what we did, we calculated map at different number of retrieved results, because as I said, people might be interested in the top 3 results or top 5 results or top 10 results. So x-axis is basically number of results that we consider for calculating the map, and y-axis is map value. And if we again concentrate on one feature, let's say the 1024 dimensional feature, we can see, so this triangle, this is with 10% of data, and we can see map at 10. If we consider about Bing search, like, so we are interested in 10 retrievals, so we can achieve around 65% map. But if we have full data, we can achieve around 77% map value. Okay. So, yeah, so conclusions. So the main contributions of the work is that this is like the first attempt to even try efficient audio retrieval technique for audio events. So, and it definitely saves millions of operations in nearest neighbor search through some kind of quantization technique. And as we saw, that even having a small amount of labeled data can be very beneficial, and it can boost the performance by even an absolute amount of 30% from the best unsupervised algorithm. And moreover, we validated our model in multiple data sets, and we found similar performance. We also validated with different features, VGG and TL weak. So in future, this is the question that Raymond asked. So this is still exhaustive search because we compare with all the elements, but there is an algorithm called the inverted multi-index, where we can actually do some kind of non-exhaustive search. And that can be, this is an off-the-shelf algorithm that can be incorporated with product quantization, that can be incorporated with DQN. Another future direction, and I already started some work and have some preliminary results, is doing the hashing or quantization part for cross-modal retrieval, cross-modal between text and audio. Ben already had this paper, and so that would be very beneficial because people might search with text, or they also might search with audio. And the last direction would be to do this efficient retrieval for hierarchical audio, so that the hash codes can also save the hierarchy information somehow, so that when we retrieve, we can have the option to back off to a course class. Yeah. So, yeah, this is it. Thank you, and please ask me questions. Any questions? Okay.
I have a question.
Yeah.
So if you had a couple of variables there, you had the number, how big your data set is,
Yes.
how big your feature dimension is,
Yes.
and then a model complexity, unsupervised versus supervised.
Yes.
So if you combine all of those together, would you say that this algorithm actually helps in what case? When you have a big data set?
Or actually helps, yeah. When we have a big data set, like order of millions, and when the feature dimension is high, at least hundreds.
Okay.
Yeah, because Euclidean distance is fast if we have like, if the dimension is 2 or 3, then it's fast. But when we have hundreds dimensions, then it becomes slow. So it will be very effective if we have a very big data set, and our embedding is high dimensional, and that is generally true because all these DNA embeddings are high dimensional. Yeah, these are the two requirements. Yeah, that it will be really nice to incorporate the inverted multi-index algorithm for non-exhaustive search. Yeah, so that we don't search the whole database, we just search a bucket. Yeah. Yeah.
So I'm assuming that the number of subspaces that you used was 8, the value of m.
So 8 was the maximum. I started with 1, 2. So yeah, 1, 2, 3, 4, and 8. Yeah. So 1 means like depending on the parameters I have, m equals to 1 means like it's similar to VQ, vector quantization. Now when I use 2, it's a 2 subspace, 4 subspace. Yeah.
In terms of performance on accuracy or MAP in this case, does it help or?
Yeah, it helps. So
subspaces?
yeah, it's a very good question because there is a relation between this number of bits and m. So I didn't go through that because it becomes too mathy and very detailed. So bit 8 means m is 1, bit 16 means m is 2, like that. So we can see when m increases, the performance increases. Yeah, it's not like strictly increasing. It might. I think it's strictly increasing. Yeah. So, but it might also oscillate because the data is not perfect data. It's noisy. Yeah.
So if you choose a different 20 samples of your data set,
Yeah.
you might see different. Are these cross-validated or?
Yeah, these are like cross-validated 20 times. So because I have 10% of the data, I chose like 10% multiple time. Like I did the training multiple time and also validation, evaluation multiple time. And also the parameters like lambda and those parameters, they are also cross-validated using 10-fold cross-validation to tune the parameters on the training set. Yeah.
So if you go back to the diagram of the algorithm, yes. Okay. So you mentioned that this technique might help retain the data similarity,
Yes.
and I assume that comes from the cosine loss.
Cosine loss, yeah.
So intuitively it makes sense.
Yeah.
You're learning and training using it, but is there a way you can visualize it and understand? Are we actually learning from the data?
From the cosine loss? Yes, I suppose there is. So since we are kind of increasing the similarity of the same classes, what visualization would be one technique. So we can basically visualize the last layer and plot some kind of like clustering scatter plot in a lower dimension using some PCA or TSNE, some kind of dimensional reduction technique. You can visualize and see how the clusters are formed between the original feature space and the learned feature space. Another way would be to calculate some kind of clustering loss, like cluster purity. Since we have the labels, like theoretically, so we can kind of calculate some kind of clustering loss and see how the purity, how pure the clusters are. Yep.
That was similar to my question. So
Yeah.
when I said removing the cosine loss, I meant put a zero weight for that.
Okay.
And just train based on quantization loss, isn't that?
Yeah, so if we train based on quantization loss, what do we do with the labels? That I'm not very.
You do not learn the labels.
Yeah.
For sure.
So because this quantization loss doesn't need label. So we have to come up with a quantization loss that needs label.
Well, then what's this? How do you calculate the loss if it's in this type?
So this loss?
Yeah.
This loss is basically the quantization error if you run product quantization on these embeddings.
So having the float point numbers versus the type.
So in other words, this loss, just think about a k-means clustering. So if I do k-means clustering on this space, I will have a mean squared error, right? That mean squared error is basically becomes a loss.
So the only part that uses the ground truth label is
The upper part.
Okay.
So that's why I was thinking like.
Okay.
So that's why I was telling that we might replace this with a different system. So for example, there is another paper by the same authors. It's actually a paper from Microsoft Research Asia, where they replaced this by a triplet loss. So a trivial kind of extension.
So how does it work for the unsupervised?
Which one? Like
You use this same pipeline for the unsupervised approach?
for the unsupervised approach? I didn't get the question properly. So
you have one supervised and another unsupervised, right?
yeah, this is the upper one is unsupervised. The lower one is unsupervised. Yeah. I mean, these are just two losses. The upper one, this needs labels to calculate the loss. The lower one doesn't need label to calculate the loss. Yeah.
And that comparison, is it in the table between the unsupervised methods and the supervised ones?
Yeah. So basically, the PQ is basically product quantization that is done directly on the features.
Without the ML.
Without the labels. So if we like really want to compare then we should compare PQ and DQN. So if we only use PQ, this is the performance, and when we use the similarity loss, this is the boost, and this boost comes from because we use labels. So basically, this we can think this as a way like. So the cosine similarity loss, it's kind of creating better clusters because they are bringing them closer. So that in turn helping the product quantization algorithm that is inherently embedded into the model. So if you have better feature space, PQ will be good. Okay. Any other question? Okay. Thank you.